So today, I am super excited to tell you all about Google Cloud and about TensorFlow 2.0, and how GCP developers can benefit from some of the great work that's being done to integrate the two. I'm Paige Bailey. I'm a TensorFlow developer advocate. And in a few minutes, my colleague Lak will come on stage, who's working very, very diligently in GCP, also doing kind of the same thing. So together, we're a tag team that will teach you everything that you would possibly want to know about TensorFlow and GCP. So starting with TensorFlow 2.0. TensorFlow has been wildly popular. We open sourced the product about 3 years ago. And since then, it's kind of grown astronomically as a tool and as a framework around the world. Each one of those little orange dots that you can see there on that map is the location of someone who has starred our repo on GitHub. And I don't know why that's like a metric that folks like to cite, but it's the case there. And so you can see it's everywhere from Europe to South America to the United States. And I think I even see a little orange dot in Antarctica, which is, deep learning on penguins. So we've had over 41 million downloads, 50,000 commits, 1,800 external contributors, really proving that this isn't just a Google internal project. It's also something the external community is very, very excited to have, too. I believe most of y'all are familiar, but we have been using TensorFlow internally at Google for the last 10-some-odd years under various names. And it's been incorporated into our most popular Google products. Everything from search to photos to Gmail, it's all using TensorFlow in order to do its inferencing for machine learning. And you can see there kind of a timeline of all of the different features that have been added over the years. We've taken Kerris, which is a higher-level API, and we integrated it a while back. We launched our alpha about a month ago at the TensorFlow Dev Summit. And then there are a number of other integrations with TPUs, with TensorFlow Hub, which is kind of a reusable machine learning model component library that you can use for free. And we'll find out all about those later on in the presentation. So as I mentioned, TensorFlow has been very, very successful within Google internally. We are using it to power our data centers and to drive efficiencies there. We use it for localization in Google Maps. We use it in Photos to support portrait mode on the Google Pixel. And the external community has built things we could have never imagined. So here, for example, you can see a code pen that was created by Taropa, one of our machine learning Google developer experts, to create custom beats, to do custom beat generation with TensorFlow and JavaScript. And that's all hosted in the browser, trained in the browser. It's delightful to see. There are also increases in medicine, right? So this is an example from DeepMind's AlphaFolds. There's kind of a protein folding Olympics that happens every year. And the first year that DeepMind entered, they were able to blow the researchers' performance out of the water, specifically for protein folding, all using TensorFlow. So historically, TensorFlow has, as I mentioned, it's been very successful. But it was also kind of painful to use. I remember the first time I tried using it in 2015, it felt a little bit like cats scratching your face. Like, it did not feel Pythonic in the slightest, So here, for example, you would have a situation where you define variables. You create a session. You initialize your variables, you start queue runners, and like this, if you're coming from scikit-learn, like this makes absolutely no sense. So with TensorFlow 2.0, we've learned a lot. We've learned that if you're going to create a machine learning framework and you want to expect people to use it out in the real world, it has to have a much more intuitive syntax. It has to be cleaner, it has to be consistent, and you have to have API endpoints that are intuitively named. So with TensorFlow 2.0 alpha, we've decided to focus on usability. We have tf.kerris as the recommended high-level API, though estimators are still around if you've been using those. And we have eager execution by default. So instead of having to create a graph before you can inspect and use it, you can now do things like add two numbers together. Wild idea, right? And you can get a response back immediately instead of having to initialize the variables and then create a session to generate the same response. We've also removed duplicate functionality. So if you used TensorFlow previously, and how many hands are those? How many of you tried using TensorFlow 1? So a good portion of the room. Excellent. I'm sorry. We apologize. I promise it's getting better. But we've removed the duplicate functionality. So if you remember, there were thousands upon thousands of endpoints, many of which did the same thing. We've sort of truncated them and bucketed them into intuitive modules. So instead of having tf.foo, we now have things like tf.math.foo or tf.signal.foo. We've also made the syntax more intuitive, and we've heightened compatibility with the entire TensorFlow ecosystem. So now instead of having multiple ways to save and export a model, everything is a saved model. And that means that it's easy to ingest in TensorFlow Lite and TensorFlow JS. And all you have to do is create something in 2.0 and deploy it to any sort of infrastructure, any sort of endpoint. We've also preserved the functionality of the full lower level API. So if you're a fan of the raw ops that you might have seen before, those are still very much available. But I do want to highly, highly recommend that you start with TF Kerris, then try subclassing Kerris modules before moving into the functionality of raw ops. We've also created inheritable interfaces for variables, for checkpoints, and for layers. And if you have any questions about those, it would be a great idea to take a look at the RFCs that have been posted in the TensorFlow organization repo. So again, just kind of a high-level architecture. We have a variety of tools for doing training, one single way to export a model, so saved model, and then you can deploy to a variety of locations. So TensorFlow Serving, TensorFlow Lite for mobile and embedded devices, including edge TPUs, TensorFlow JS for deployment in the browser. You can also train using TensorFlow JS. And we have several other language bindings, so everything from C to Rust to Swift and more. As the training workflow, if you have experience using machine learning, this probably looks very familiar. Historically, again, it was very, very difficult to ingest data, especially structured data, into TensorFlow projects. Now we have tools like tf.data and tf.data.datasets that make that process very, very straightforward and simple. So for example, if you wanted to load data using TFDS, all you would have to do is assign a variable to that data set, create some sort of ingestion function, and then divide it into training and test sets. So again, if you're from the scikit-learn community or if you're from the R ecosystem, this syntax looks much more intuitive than having 100 lines of boilerplate code in order to just ingest a CSV or a table from a database. We have a variety of data sets that are freely available as TensorFlow data sets. So massive ones that reach search scale, and then also smaller ones that are more typically used for machine learning projects. So for example, the Titanic data set, MNIST, the IRIS data set. But I highly encourage you to take a look at all of the ones that are available on the website. And of course, TensorFlow loves Kerris. So how many of you have used Kerris? Somehow there are fewer hands than the number of people that said that they've used TensorFlow, and that breaks my heart. Oh man, okay, cool. So that's everybody's homework for tonight. Your homework is to go and try out Kerris. So I mentioned before, I think, that I started using TensorFlow in 2015 when it was first released. And it was excruciatingly painful. And the only reason that I started using it more was because of this higher level API called Kerris that was authored by a gentleman named Francois Cholet. And what it does is, instead of having the confusing 300 lines of code in order to do a thing, suddenly your project looks a little bit more like this. You import TensorFlow, you assign a training and test data set, and then you can build a model with just 5 lines of code. So again, if you're a fan of scikit-learn, this should look pretty simple. All you have to do is define some layers. If you've taken any sort of deep learning class, you can probably recognize that this is MNIST because there's a softmax layer telling you that this is a classification task with 10 options for output. You can define some optimizers, the loss, the metrics that you care about, and then you go through the training process. And that's all. To build a deep learning network, that is all you need, 10 lines of code. And since we're Google, we wanted to make it scale. And to make it scale, it's as simple as adding 2 additional lines. So with distribution strategies, you can scale across a cluster of GPUs, a cluster of TPUs, a cluster of CPUs even. And it's just as simple as placing your model in a with strategy scope. It's great also to not have to be responsible for doing the entire training process yourself, right? Like only a few companies have access to massive amounts of data. And deep learning has been proven that the more data you have, the better. So in order to sort of give a leg up on that process, to accelerate the quality, the accuracy, and the training of your machine learning, we've created something called TensorFlow Hub. And think of this as a sort of open source library of models and model components. So Google has open sourced hundreds of their most useful tools, everything from natural language processing to image classification to video analysis, from speech to text, and a variety of languages. And they've made them freely accessible for the public. All you have to do is import each one of those model components into your TensorFlow project, and suddenly you can go from taking 2 weeks to train on a massive data set to taking something like 7 minutes through the power of transfer learning. And I mentioned before as well, for folks who are more used to having sort of highly specific and specialized models, Kerris might feel a little bit too high level. But if you need to go a little bit lower, you have the ability to do subclassing. And so this is building a custom encoder for machine translation, focusing on implementing the computational algorithm. You can even customize the training loop to get full control over the gradient computations and your optimization process. And of course, all of this is able to be visualized within TensorBoard. With TensorFlow 2.0, we've even given you the ability to embed TensorBoard within Jupyter Notebooks and within Google Colab. And we've created built-in performance profiling tooling for TPUs and also for GPUs in collaboration with our partners at NVIDIA. We've boosted the documentation. So documentation is always something that people are asking for. Better API endpoint examples, better tutorials, quick starts, things that you can copy and paste the same way that you would copy and paste from Stack Overflow. So we've improved that. And we've also increased the performance. So here are some metrics that might be interesting for folks to go and try out on your own data. We've also added something to the effect of 60 additional projects to the TensorFlow organization repo. So we've come a long way since we open sourced in 2015. Everything from TensorFlow probability for statistics-focused analysis and Bayesian methods, to TF agents for reinforcement learning, tensor to tensor, TF ranking for sort of ranking problems, TF text for natural language processing should be released later on this year, TF federated and TF privacy for secure computation, and more. So if you're interested in anything, you see in the repo, please feel free to drop me a line and to start contributing. You can deploy anywhere, again, mobile and edge devices, servers, browsers. With TensorFlow Extended, we've built an end-to-end machine learning pipeline, everything from data ingestion to training to retesting your model's performance over time to deploying it. and deploying it in a variety of ways. So this was always the most frustrating piece to me as a data scientist, was I would create this beautiful model. It would be written in Python or it would be written in R, and then I would hand it off to a DevOps team to do data science, and they would refactor the entire thing into Java or to C++. And it would be really, really difficult to make any sort of modifications to that model over time. And it would also be really, really difficult to obtain accuracy metrics or to understand kind of the provenance and the lineage of my data as it was going through the retraining process, to make sure that I was training on data that was in the same format, the same type as the data that it had been trained on initially. And TFX, again, it's what we use internally to do all of this end-to-end machine learning process. And it's all completely open source. So if you want to use it, there's nothing stopping you. You can take a look at our GitHub repo and use it on your own infrastructure before deploying it to a cloud infrastructure. I mentioned before we have TensorFlow JS, a lot of pre-trained models there. And again, with TensorFlow 2.0, we're focused on an entire ecosystem of products. So not just something that you can train locally on your laptop, not just something that you can train locally on a cluster, but to any endpoint that you can imagine for deployment, and also integrating with a lot of other tooling. And the question that I'm sure everybody's concerned about, how do I upgrade? Unfortunately, 2.0 code is not synonymous with 1.x. Even if it looks exactly the same, you will still need to make an upgrade. But we've decided to make it as easy as possible for you. And that's because all of our colleagues within Google are also migrating right now at the same time. So if you do it right now, you're on the bleedingest of edges. Yes, so upgrading is as simple as running an upgrade script. All you have to do is take the TF upgrade v2 tool, define a Python file that you want to upgrade, or a directory of Python files, and then a location that you would like to specify for that output. It does a variety of things, and we'll take a look at that now. So for example, here, you would export a Python file or a Jupyter notebook. Both are supported thanks to one of our machine learning GDEs. You run the upgrade script with TF upgrade v2, and you specify an output location for that Python file. And you get a report.txt generated from the tool. And it tells you everything from it renamed some of the endpoints. So again, that reorganization process that I was talking about before, where we're cleaning out the cruft. It tells you that it added some keywords to a function called tf.multinomial before it renamed it. And it tells you that it renamed a couple of other symbols to tf.compat.v1, which just means they don't have a one-to-one equivalent within TF 2.0. But you do have an escape to backwards compatibility mode. And then once that's done, you can run the script exactly as you would before. So really, we wanted to make sure that the upgrade process was as simple and as straightforward as possible. If you have existing 1.x models, you should be able to run this and get back something that looks like 2.0. And if you have any questions, confusions, or snags, feel free to file a bug on GitHub and to let us know about it. We have a testing and migration support hour every week at 2:00 p.m. Pacific time, and we would be delighted to have you attend. You would be attending with Google engineers. And we're all delighted to hear about the experience that you're having using 2.0. All of our progress is available online on GitHub as in sort of a public progress tracker. We wanted to heighten the transparency, and we know that a lot of people sort of care about the functionality and when it's going to land. So please take a look at that. And also, TensorFlow 2.0 is all about community. So if you would like to win a free ticket to something called TensorFlow World, or if you would like to present your TensorFlow 2.0 project directly to the TensorFlow engineering team, feel free to take part in our Powered by TF challenge. The URL is there. And we also have a Udacity course that has been released just recently. So this is 15 modules, completely free. Highly encourage you to go and take a look at it. It was a lot of fun to create. And let us know if anything is interesting to you, or if there's anything else that you would like to see. And with that, I'm going to welcome my colleague Lak to the stage, where he will tell you all about how you can use TensorFlow with GCP.
Thank you, Paige.
Thanks.
Thank you. Thanks, Paige. So Paige mentioned a few things, right? The key thing being that with TensorFlow 2.0, we focused very much on usability and simplicity, about taking the things that used to be very hard in TensorFlow 1 and making them easy. And one of the things that used to be very hard was running TensorFlow models on TPUs. You had to basically rewrite everything. So yes, TPUs were faster, but it wasn't that you could just take your code and run it. Your estimator models being moved to a TPU is very hard. So we're very, very, very happy to say that you can now run Kerris models pretty much as is on a TPU, right? So we talked about how TensorFlow loves Kerris, so do TPUs. And the cool thing is that with TensorFlow 2.0 being alpha, many of these changes are already available to you in the stable version of TensorFlow. So TensorFlow 1.13, if you're using it today, you can start using some of these things that we're talking to you about, and you can upgrade as TensorFlow 2.0 goes into beta and goes into GA. So why do we need TPUs? And this is one of my favorite graphs, and it's something that you want to kind of understand when we look about machine learning, right? Effective machine learning requires large data sizes. We all know this. Everyone says, yeah, we need lots of data if you're going to do ML. But no one quite tells you what we mean by large amounts of data, right? So look at the x-axis on that curve. That's the size of your data. And the y-axis is your error rate. Error rate goes down as your data size goes up. Cool. But how does your data size go up? It's 2 power 20. This is the translation model, but the same kind of effect holds for other types of models. It's 2 power 20, 2 power 21, 2 power 22. So what's happening to the data each time? It's doubling, right? We're not talking about 10% more data. We're talking twice as much more data, 4 times as much more data, 8 times as much more data. So that's number one, right? So if you're basically looking at you want to build effective machine learning models, you need large amounts of data for anything beyond toy problems. If you're going to be building custom ML models, you need large amounts of data. The second bit, right, is that over time, the way we've taken advantage of large amounts of data is that our models have become more and more complex. So if you look at the size of your model, AlexNet was what launched the whole deep learning revolution, 2013. That was a very simple, like a few layers. And then when we get to neural architecture search, which is a thing that powers AutoML on Google Cloud, the difference in compute is 10,000 times. Okay? So put those two things together. You basically have now 32 times more data, and you're using models that require 10,000 times more compute. That's the machine learning challenge when it comes to running infrastructure. Okay? So that's kind of why you need application-specific chips that are focused on machine learning, and that's what TPUs are. And TPUs version 2 and 3 are available on Google Cloud today, with version 3 providing 8 times the power of version 2. So the idea is that when you want to develop on TPUs, you basically develop with Jupyter, and you just develop in a Jupyter notebook, and this Jupyter notebook is basically running in a deep learning VM, and the deep learning VM is connected to a cloud TPU. And so you're basically developing in your very familiar environment, and you're basically building ML models on those. Okay? And as I said, the models that you're building now can be just Kerris. Right? You're basically building tf.Kerris models, and they run on TPUs. Okay. So here's an example of a notebook that essentially works the same on both CPUs and GPUs. So here, I'm launching a compute engine instance, and then launching Jupyter Lab. I'm into the Jupyter notebook. I've Git cloned a repository. I've opened up the repo, found the TPU. So these lines of code are different. But once we found the TPU, I can basically take advantage of reading the data. It's all exactly the same notebook. It's exactly how we would write a Kerris model. if you are running it on a CPU or you're running it on a GPU, with this one difference that we're using a TPU distribution strategy. Right? So where you would normally be using a mirrored strategy for a GPU, you can now use a TPU distribution strategy. And where you would normally call model.fit, I'm calling TPU model.fit. It's exactly the same Kerris kind of code. Right? So you write your Kerris code, and the same notebook, we're now going to basically change it. So it's all of the same stuff. And then I'll go ahead and shut off the TPU. I will launch this whole thing on a GPU machine and start this whole thing again. And now, at this point, the TPU part is done. It has trained the model. It's done image classification. I'm shutting that off. I'm starting a GPU at this point. I'm reloading that notebook. And this time, I'm just running it 10 times faster, right, just to save time. But the idea is that the exact same notebook works on both GPUs and TPUs. So that essentially makes that you have the ability to run extremely fast things faster. So why would you use a TPU, right? One of the cool things is, normally when you go from one GPU to a second GPU, do you get twice the performance? No, right? Why don't you get twice the performance? Because there's some network overhead, and so you don't get, so if just because you put 40 GPUs in a job, you don't get 40 times the performance. You tend to basically start plateauing because the network overhead starts to take over. The cool thing about a TPU is that even though in that notebook we showed you running it on one GPU versus running it on one TPU, you can basically expand this out to running on 128 chips on 1/8 of a TPU pod, or go up to half a TPU pod with 512 chips. And you basically get linear performance because of the interconnect within the TPU. Right? So the real benefit is basically driving back to the first point that we made, that when effective machine learning requires extremely large amounts of data, so you need to basically get a pipe of data that's coming in, and you're able to read it very, very, very fast. So you're able to use much larger batch sizes and basically get more accurate models, and not only get those more accurate models, get much better performance on it. Okay. So this is basically the end result. So if you basically take a full TPU pod, you basically get about 200 times the performance of a GPU at lower cost. And the cool thing now is that with the simplicity of TensorFlow improving and the ability to use Kerris models, you're able to do Kerris models on a TPU. The second big aspect is what Paige also kind of talked about, the TensorFlow extended. So we talk about machine learning, and we basically talk about the machine learning model. But the machine learning model that we build is just one part of a much larger pipeline. And as we talked about, we don't want to have to go rewrite everything in order to put it into production. So the way this is done at Google is to use TensorFlow Extended. And we published a paper on this back in 2017 that was about how we build a TensorFlow-based production system. And the key thing is that there is a trainer in the middle. That's the machine learning code that we all talk about. But before that, you have preprocessing and you have validation. And after that, you need to evaluate your model, and you need to serve it. All of these components form the production system for building and deploying TensorFlow models. Last year, we had already open sourced a few of these things, right? And some of the parts around it, like the tuner, is a hyperparameter tuning that's part of our AI platform. It's part of our ML engine. Logging is provided on GCP by Stackdriver. We had also open sourced the transformation, which was TF Transform, which on GCP you can run at scale using Cloud Dataflow. And we had open sourced TensorFlow Serving, which is how you take a saved model and you deploy it. And you basically can do that with on our AI platform using predictions, using ML engine. So you basically have the open source aspects, and you have the ways to run them on GCP. So that's what we had last year. Now this year, we basically have also open sourced the validation piece and the evaluation piece. And of course, the number 3, the trainer part was the TensorFlow model that was always open source, and you could do it. But at this point now, the entire TFX pipeline is open sourced, and you can run it at scale using managed services on GCP. So let's quickly walk through those. Okay, so to kind of say, what are these? Let's say, for example, a validation piece. Let's say you're doing a healthcare data set, and you have a column named last diagnosis. You might want to say that this last diagnosis is a ICD-10 code. And ICD-10, like, there's a bunch of different healthcare diagnosis things, and each of this has a particular vocabulary. And you might want to be able to say, based on my data exploration, in my training data set, about 3% of this is invalid. Right? You basically explored your data, and you found that that is the case. At production time, what you can say is that now this is my schema that I've discovered during the data validation by looking at all of my training data sets, and we can basically provide a threshold. As long as during serving, less than 5% of the inputs that come in are not in my vocabulary, it's OK. But everything that's not in my vocabulary, write it to an anomaly place. And then we can monitor these anomalies so that if the vocabulary ever changes, people start putting in new diagnosis codes that you don't know about, you now know about it because they show up in these anomalies. That's the point of the data validation piece that you put ahead of your preprocessing. Okay? And the way this works is that, again, this is the first part of the TFX workflow. We're basically going ahead and getting the data set, taking the data, this is the training data and the validation data, and then we're basically importing TensorFlow data validation and using that, and this is just a CSV file, and I'm basically doing generate statistics from CSV. Right? So basically reading all of these files, telling the TensorFlow data validation to go ahead, and in this case, I'm asking you to sample just 10% of the data. Obviously, we can do the sampling fully, and this is a beam pipeline that runs on Dataflow and creates this graphic for us by looking at all of the columns and basically computing statistics, giving us quantiles, giving us a distribution of these, how many of these are missing in the training data set. Right? And we do this for both the numerical data. We also do it for the categorical data. In this case, the origin, it's a flights data set. There's like Atlanta is the most common airport. We take that data, and if you have some data that has a vocabulary like the carrier, it knows all of those vocabulary items. It takes all of those things and saves them in the schema. And we can basically go ahead and take the schema and save it. And this schema can be used later on during the production workflow as well. So this is the schema that you're creating from your training data set, and this schema is basically going to get used as part of your production pipeline to know when there's an anomaly that has happened. Okay. So the next bit, once you've done the data validation, is to do the pre-processing. So you're basically going to, and this is something that we've seen before, where we take our data and we scale it, we find the vocabularies, we do one-hot encoding of it, and that is with TF transform. And in this case, for example, we say that we have our aircraft data, and we may have like airports. What are the airports, and how do you one-hot encode them, et cetera? This is TF transform. It's exactly what existed before. Okay, so in this case, I'm basically creating a pre-processing function. And unlike the data validation, in this case, I'm explicitly showing you the beam code. So we have helper functions to make it easier, or you can basically write the beam code yourself to basically do things that are much more customized. But in either case, you can run the pipeline on Cloud Dataflow. And at this point, you basically have a pre-processed data with the results of this pre-processed data being written out. So the TF transform writes out the transformed trained data. It takes the test data, writes the test data also out, and it writes out the transform artifacts. How should I scale the input values? What are all the schema values that come in? How should I know that things are anomalies that I need to know about? And all of those are now stored, and they can then be used to basically train your typical model. So that model, again, the training is exactly the same. In the interest of time, I'll skip that, and I'll move to the next bit, which is after you've trained your model, you want to do your model analysis. How does that look like? So in the model analysis case, I'm basically saying that, OK, so this is the part 4 of it. And I'm basically doing the model analysis where I'm saying that I want to slice the output of my model based on certain attributes. I want to see is the accuracy of my model, does it vary depending on which airport we are flying from, right? So I'm basically going ahead and running the evaluation, but I'm now doing the evaluation not on the entire evaluation data set, but in various slices. Okay, so watch for that. The slices will come up in a little bit. Okay. So I'm importing the TF model analysis and then preparing the data slices for evaluation. Okay, that's the next thing that's going to happen. Okay, right, there's a slice spec, and I'm saying that I want you to slice the evaluation by the origin field, by the destination field, and by the carrier field. So I have 3 different ways that I want you to slice the evaluation. And then when I run my evaluation, I'll basically get metrics for each airport that is an origin, each airport that's a destination. And obviously, this depends on your data set, right? You can slice it by customers, you can slice it by country, you can slice it by different kinds of scenarios. And you can basically monitor how well the performance is. And the result is basically you can go ahead and visualize those rendering results. So that's basically the model analysis bit. The last part is serving the saved model, and that remains exactly the same. We have a G-Cloud way of basically taking a saved model and serving it out for predictions. So that part, again, it remains exactly the same as we used to do before. You say G-Cloud ML Engine, create a version, go ahead and deploy it for prediction. You send in a JSON input, and you get your predictions back. But the cool bit is, now that this deployed model takes advantage of all the pre-processing, takes advantage of all the data validation steps that have been done, and these anomalies are getting written out so that you can go ahead and monitor them. So basically then, right, this entire pipeline is now all open source, and it's available to be run at scale on GCP. So as a quick summary then, right? What's new in GCP and how do GCP developers benefit? Number 1, to summarize what Paige talked about, TensorFlow 2.0, you get eager execution, a lot less code, you get to use TF data pipelines, you get to reuse TF modules, and you get to use distribution strategies in Kerris. And you can try out TensorFlow 2.0 alpha on our notebook instances. Right? So you can basically launch Jupyter on GCP, try this thing out. And it's very easy to migrate from 1.x to 2.0. Right? So you basically have that upgrade script. So you can use that as a start. And over time, you can change the things for which there is no direct one-to-one mapping, the things for which we do tf.compat.v1. tf.compat.v1 will continue to work in 2.0. It's not that you have to change it immediately, but it's going to be a best practice for you over time to remove the compat.v1 from your code. Second big improvement is the cloud TPUs. Right? So we basically have the cloud TPUs are hardware accelerators for TensorFlow. They're faster, they're less expensive, and much more scalable than GPUs. And the really cool bit is now you can write TensorFlow models for the TPU, and those models can be written in tf.keris. And that makes it much easier, and as we showed in the demo. And it's available on notebooks, it's available in ML Engine, it's available in Kubeflow pipelines. You can access your TPUs from all the different environments from which you can run ML models on GCP. And lastly, TensorFlow Extended, which basically builds out an ML ecosystem beyond just the training piece. Now you have data validation, you have pre-processing, we have serving, and you have model analysis. We've completed the story now, where last year we had only 2 pieces of it. Now we basically have completed it. And you can take advantage of that to run things at scale using Cloud Dataflow and using Cloud ML Engine. And again, it's available on Kubeflow pipelines, and it's available on Airflow. Thank you.